Welcome you all in my next lecture. So in my last lecture I talked about the concept of limit for several variable functions, and I have discussed some examples and then the corresponding concept of component functions, and there is an interplay between the existence of limit of the original function and component functions. Now this time I will talk about the more examples of existence of limit, and then I will talk about if time permits then the concept of continuous functions and corresponding interplay between the original functions, existence of continuity of original functions and component functions. Okay, now existence of limit I talked about. So now in my last lecture I talked about that okay, if I want to show that limit does not exist, then what you do, suppose the definition of the function is given, you identify the component functions and then you say that okay, if the component function limit exists, then the corresponding original function limit exists and vice versa. So now there are another way you can kind of see the existence of limit. So earlier if you recall that in terms of Cartesian coordinates I talked about the existence of limit, or either using the kind of definitions or different paths, that kind of things. Now you can have another one like converting other coordinate system and then find the limit. What does it mean? That means instead of Cartesian coordinate system, if I say have a like spherical coordinate system or polar coordinate system, using that also you can talk about the kind of existence of limit here as well. For example, if I want to compute the limit of this kind of functions like limit xy approaches to 0, x square y square divided by x square plus y square. Now this kind of functions, if you see like that kind of numerator and denominator like square of x or square of y, and like in the denominator you have x square plus y square, then you can guess that means instead of doing with the Cartesian coordinate system, if I change it to polar coordinate system, then things will be easy to prove that. So that's what I have wanted to convince you, is that compute this converting into a polar coordinates. That means I want to find the limit of this. So what I want to do, I want to change it to polar coordinates. That means what is this? That means x is equal to r cosine theta and y is equal to r sine theta. If I change it to x is equal to r cosine theta and y is equal to r sine theta in polar coordinate, then you put the value of x and y here, then it will be like this one, r4 cos square theta sine square theta divided by r square, and this is exactly equal to 1 r square get cancelled, this is same as this one. But I know that cos square theta and sine square theta is always lesser equal to 1. So therefore this limit always dominated by this limit, and what is the limit? Limit r approaches to 0 plus r square, which is nothing but 0. So therefore left I am having 0 which is lesser equal to this limit, lesser equal to 0. So therefore the limit has to be equal to 0. So therefore limit x y approaches to 0 0 x square y square divided by x square plus y square, it's exactly equal to 0. That's what I have written. So what I am trying to say is that by looking at the functions, if you change the Cartesian coordinate to some other coordinate like say polar coordinate or cylindrical coordinate or spherical coordinate, sometimes calculation is easy to show that whether limit will exist or limit does not exist. So that's the main point. Okay, so this is again another kind of equivalent criteria for the existence of limit. This is called sequential criteria for the existence of limit. I think similar sort of things you might have seen in the real analysis case. That means if limit exists, so that means if any sequence approaches to that point, that means suppose I want to check the existence of limit of function f at some point, say some point say capital subset on x star in the real case. So whatever sequence if converges to x star, the value of f, all those sequences also converges to same point. So similar kind of results is also true in the context of kind of several variable case. So what is that? So this is the theorem. So let capital F, which is a map from S subset of Rn to Rm, is a functions. Let x star be the limit point of S. So let L be the point in Rn. So then what is the statement? Statement says that limit x approaches to x star capital Fx is equal to L. That means limit of the original function exists and value is capital L if and only if for every sequence capital Xk in X, but you just note that Xk is not equal to x star for all cases. I mean it should not be a sequence like x star x star x star. So if I have every sequence Xk converging to x star, then the corresponding sequence f of Xk should converge to L. So that means if I want to check the existence of limit of capital F at some point x star, what we will do, whatever sequence converging to capital X star, the corresponding sequence, that means corresponding value of the sequence, that means f of xk, it also should converges to the same limit. If this is true, then I will say the limit. This is the kind of equivalent criteria for the existence of limit. This is sometimes called sequential criteria for existence of limits. Again, this is a kind of useful like to show that limit does not exist. Suppose I want to show that the limit does not exist, that means at some point, suppose the point x star, what you do, take two different sequences xn and yn, both converges to x star, consider the sequence capital F of xn, capital F of yn. So that means suppose you have a point x star, suppose I have two sequence, suppose this is xn which is converges to x star, you have another sequence, suppose yn which is also converges to x star, but somehow prove that f of xn converges to one point say a1 and f of yn converges to another point b1 and which is different, then you will immediately say that limit does not exist. See, this is actually to show the limit does not exist, these kind of things are useful. Okay, now once I have the existence of limit for several variable functions, now the corresponding concept of limits also come, iterated limits of scalar valued functions. Scalar valued function means what? So I suppose let f be a function, so for simplicity I am considering a subset of R2. So let f be a functions from R2 to R is a real valued functions of two real variables. So now I want to talk about the existence of limit. So let x naught y naught be a limit point of S. Then what is this? So what is the meaning of this object? So this object meaning is that, so what is the meaning of this limit? This limit is that, so what I am doing is that you think about x is like constant variable. So think about x is constant, so therefore consider the function x, or like suppose x is fixed, suppose this x is fixed, okay. So now consider the function y goes to f of xy. So now this is what kind of function? This is a function from R to R. Now you can talk about the existence of limit as y approaches to y naught. So therefore keeping x as a fixed variable, then I can think about the limit of real valued functions of real variable, that means limit y approaches to y naught f of xy. Once I have that, then what I will do, that means at each x limit exists, that means this is a function of x, then I can talk about limit x approaches to x naught. So this, if this limit exists, similarly you can flip it, that means first you keep y as a fixed variable, then talk about the existence of limit for this single variable x approaches to x naught. Once I have that one, then you take the limit as y approaches to y naught. So if these two limit exist, then I will say that these are called the iterated limits of it at AB. So at AB it should not be AB, it should be x naught y naught. This is a mistake. Is that clear? So what I am doing is that, so I am starting with a real valued functions of two real variable. Then what I am doing, I am first keeping x variable fixed. So I am thinking about is a functions from R to R, that means keeping x fixed, think about a functions y gets to f of xy, then I can talk about limit y approaches to y naught f of xy. So it will give you some value, so some value it will give you, but since x is fixed, so it should depends on x as well. If this is the case, then I will take the limit as x approaches to x naught. So that means this is same as limit x approaches to x naught dx. And if this limit exists, suppose this is exists, then I will say that this is finite, or this is called iterated limits. That means keeping x variable first, then take the limit as y approaches to y naught, then take the limit x approaches to x naught, and vice versa. The vice versa means other way around. That means first keep y variable fixed, take the limit x approaches to x naught, then take the limit y approaches to y naught. So if this limit exists, then I will say that these are the iterated limit of f at x naught comma y naught. And what is this? This is the symbol I already explained. So this is kind of existence of limit of several variable function. That means if I have a function f from R2 to R, if this limit exists, then I will say that this is the double limit. So the limit I have already defined, that is called the double limit. So therefore the natural question, so I have defined the already double limit or existence of limit I have already discussed. Now I have two sets of limits, iterated limits I have discussed. Okay, how we can define the iterated limits. So therefore the natural question is, what is the relation between the existence of these three limits? That means this is one iterated limit, this is another iterated limit, and this is the double limit. Is there any relations? Let's see some example first. Okay, so this is the note on iterated limits and double limits, what it says. So this is very important. So first, existence of the double limit does not guarantee the existence of iterated limits. That means I have an example of a functions where the double limit exists but iterated limit does not exist. Second one, existence of iterated limits do not guarantee the existence of double limit. I will also have an example where the iterated limit exists but the double limit does not exist. And finally, third one, if the double limit along with iterated limit exists, then they are all equal. That means the value of the double limit is exactly equal to the value of the iterated limits. So this is very important. So that means existence of iterated limits will not guarantee the existence of double limit. Existence of double limit will not guarantee the existence of iterated limits. However, if the double limit exists and the iterated limit exists, then all values are equal. That means the value of the double limit is exactly same as the value of the iterated limits. Let's see some examples. So look, first example, it says that double limit exists but iterated limits do not exist. Okay, let's see some example. So I have a functions f which is defined like that. This is a functions, it's a functions from where to where? It's a functions from R2 to R. So first let's see that double limit exists at the point 0, 0. So first see the existence of double limit. So now I think I already discussed the existence of double limit, if you remember in my earlier lectures. So how do you prove it? So this is very simple. That means I have to estimate x sine 1 by y plus y sine 1 by x. Okay. So this is f of xy minus 0, which is lesser equal to mod x plus mod y, right, and which is lesser equal to 2 times square root of x square plus y square. Then use the definition, given epsilon positive, choose delta is equal to epsilon by 2, then I can make this is less than epsilon whenever 0 less than x square plus y square, which is less than delta. So that kind of calculations or that kind of discussion I already made in my earlier slides. So therefore this will implies that this double limit exists and this is exactly equal to 0. Let's see the existence of iterated limits. Okay, so let's see first iterated limits. That means I am keeping y as a fixed variable, taking the limit x approaches to 0, and then I will take the limit y approaches to 0. And second one, I will keep x as a fixed variable, taking limit y approaches to 0 by thinking is a function of single variable, that means real valued functions of real variable, and then finally I take the limit x approaches to 0. Okay, let's see. So limit x approaches to 0, so I am doing this part. So limit x approaches to 0, f of xy. What is f of xy? This is my f of xy. X sine 1 by y plus y sine 1 by x. So therefore I can distribute the limit. So that means limit x approaches to 0 plus limit x approaches to 0. But this limit is equal to 0, that we know because this is a bounded function, not an issue. And x approaches to 0. But what will happen this one? This one we know that in the single variable case that limit x approaches to 0 sine 1 by x limit does not exist, does not exist, does not exist. That we know. Why? So you can prove it by sequential criteria. You can say that you have two different sequences, both converges to 0, then the corresponding sine 1 by x and those sequences converges to two different limits. That is very standard that we might know in the single variable calculus. So since limit x approaches to 0, sine 1 by x limit does not exist, so therefore this limit does not exist and therefore this limit does not exist. Since limit x approaches to 0, this limit does not exist, so and therefore automatically limit, if I take the limit y approaches to 0, this certainly does not exist. In the same way, you can prove that instead of taking limit x approaches to 0 first, if I take the limit y approaches to 0 first, same way, limit y approaches to 0, sine 1 by m does not exist. And hence, limit x approaches to 0 of limit y approaches to 0, f of xy does not exist. So this example ensures you that even if the limit of f double limit exists, but the both iterated limit does not exist. See other examples where we have the iterated limit exists, but the double limit does not exist. So this is the example. So let's take f is equal to x square plus y square, xy non-zero. Now I want to talk about the existence of double limit at the point 0, 0 and corresponding iterated limits. So first you calculate the iterated limit. Okay. So first you calculate limit y approaches to 0, f of xy. What will happen? So limit y approaches to 0, f of xy means x square plus x square by y square. What will happen? Y approaches to 0. So that means it should be exactly equal to 1. Because y approaches to 0 means x square by x square, this is 1. So therefore this is a constant function. Now if I take the limit, say x approaches to 0, that means this is limit x approaches to 0, then this is 1. What will happen the other one? Suppose if I take the limit x approaches to 0, then by looking at the function it goes to 0, and therefore limit y approaches to 0, that is 0. So therefore both iterated limit exists. So first one value is 1, second one value is 0. But let's see whether the double limit exists or not. So that means limit xy approaches to 0, f of xy does not exist, and that is kind of straightforward, because look at the functions. This is x square divided by x square plus y square. As I already said that if I take this kind of path, so that means I have this my origin, this is my 0, 0. If I approach to the origin the path y is equal to kx, okay. So in y is equal to kx, if I approach, just put the value y is equal to kx, then what will happen? X square by x square plus y square, which is same as x square by x square by k square x square. So what will happen? This is 1 by 1 plus k square. So that means if I approaches to 0, 0, two different paths, say y is equal to k1x, y is equal to k2x, then the corresponding value of the function approaches to two different limit. One is 1 by 1 plus k1 square, another is 1 by 1 plus k2 square. So that means I am approaching to the origin two different paths, but the value of the function approaches to two different limits, and therefore limit does not exist. Because I know that limit exists whenever I approaches to the point, whatever directions the limiting function should exist, the value of the limiting function should also be the same. Here it is depends, and therefore limit does not exist. This is one example. Another example, take this kind of functions, f of xy is equal to x square plus y square, x square y square divided by x square y square plus x minus y whole square. Again, you can easily check that if I take limit y approaches to 0, this is a 0 function, so therefore limit is this x approaches to 0 also 0, limit x approaches to 0 f of xy, this is also 0 function, so therefore if I take the limit, this is also 0. However, the double limit xy approaches to 0 does not exist. Again, you just check, if I take y is equal to path, that means if I take, this is my origin, again if I approaches to 0 in this direction, or if I approaches to 0, y is equal to 0 means if I approaches to via x axis. So if I take two paths, that means y is equal to x, this is y is equal to x path, and this is y is equal to 0. So they are both goes to 0, 0, but the corresponding value of the functions limit different, because if I put y is equal to x, it will give you some value, if I put y is equal to 0, it will give you 0. So that means even if I approaches to 0, 0, two different paths, but value of the function approaches to two different points or different limits, and therefore limit does not exist. So let's see examples. So do they contradict the following theorems? In other words, what I'm trying to say is that look at the statement of the theorem. What it says, let f be a real valued functions defined on a neighborhood of point x0 y0 city of R2, except possibly at the points. Of course, I want to talk about the existence of limit at the point x0 y0. As I already said, it not necessarily it should be a point in the domain of f. Suppose that limit xy approaches to x0 y0, f of xy is equal to L. That means suppose the double limit exists, and moreover one dimensional limit. That means one dimensional limit means keeping y variable fixed, think about is a functions of R to R, and think about the limit x approaches to x0 of f of xy. Similarly, keeping x is fixed, think about the functions y goes to f of xy as a function from R to R, because x is fixed, and think about the limit y approaches to y0. So if the double limit exists, if the one dimensional limit exists, that means if limit x approaches to x0 f of xy, keeping y variable fixed, if this limit exists, along with keeping x variable fixed, limit y approaches to y0 f of xy exists, then the iterated limit exists. Not only that, value of the iterated limit is exactly equal to the value of the double limit. Okay, so this is the theorem. So that means to ensure that the existence of double limit implies the existence of iterated limits along with the same value, I need the existence of double limit along with the existence of one dimensional limit. That means limit x approaches to x0 f of xy and limit y approaches to y0 f of xy. If these two things limit exist, then I have all iterated limit exist, and value of the double limit is exactly equal to the value of the iterated limits. Okay, so I think I should stop here. This is kind of little bit about the existence of limit of several variable functions. Couple of equivalent criteria I have given. I have given some examples. Then we have discussed the concept of iterated limits, double limits, and that sequential criteria. Then corresponding existence of the limit of original functions. What is the interplay between the existence of limit of the original functions and the component functions? So these are the things we have seen. So that's kind of bit about existence of limit or concept of limits in the context of several variables. In my next lecture, I will talk about the concept of continuous functions for several variable functions. So I think I should stop here. So next time, in my next lecture, we will talk about the concept of continuous function. Thank you.